let's have a quick look at factor analysis and what it means and why we even want to use it. Now, there are two different perspectives on this. You can either go from theory to observation or from observation to theory when you try to identify why it is you would want to use factor analysis. So let's have a look at the perspective from theory to observation. The reasoning goes like this. We are often interested in examining the relationship between concepts that are abstract and cannot be readily observed, for example happiness or leadership. In order to tap into these constructs, we measure their manifestations which can be observed directly. And then we use factor analysis to derive scores on the unobserved latent constructs of interest. Now let's have a look at the other perspective, from observation to theory. Factor analysis can be seen as a statistical method used to describe variability among observed variables that are correlated in terms of a lower number of unobserved variables, which we call factors, so these are our latent variables. For example, it is possible that variation or covariation in 6 observed variables mainly reflect the variation in a single underlying variable. Now, both these perspectives point to the same kind of setup, which is as follows. You have obtained scores on questionnaires from your participants. These scores are actually a reflection of how they are inside. For example, you might get high scores from a person who is very happy, and low scores on the scale of happiness from someone who is not so happy. What this means is that the scores are the outcome of how you feel inside. It could be happiness, love, or other constructs that are not readily observable directly. So in summary, answers to questionnaires are a reflection of how you feel inside, which means they are a function of how you feel inside. This should already make you think that the questionnaire items must be outcome variables, and the latent variables or the factors must be some kind of predictors, because how you feel inside should predict your scores. Now, how would we visualize this if we wanted to put it in a diagram? Let's say we have a scale of happiness, and it has these 4 items, which people have to endorse. 1. I am interested in other people. 2. I feel that life is very rewarding. 3. I find most things amusing. And 4. I often experience joy and elation. So your participants' scores on these items are what you observe directly, and they are a function of an unobserved latent trait, in this case happiness, but also a function of what we call error. Notice that the questionnaire items are represented by rectangles in the figure, whereas happiness and the error terms are represented by ellipses. This is the standard way of drawing diagrams, which really helps distinguish between what was observed directly and what was not. Importantly, even though the terms on the left are labeled error, they don't necessarily have to be only a function of noise. They could be a function of other things that you did not directly measure in your study, or even other latent factors that would be unobservable. For this reason, sometimes people call the error terms uniquenesses. This comes from the perspective that variation in people's scores on each item is split into a proportion of that variance that is explained by the latent trait, and another leftover proportion that is leftover, it's unexplained. This is said to be explained by error, but some people just call it residual variance. When you look at this diagram, you probably see all of these straight arrows here and all of these other straight arrows here, because this depicts a linear relationship, just like linear regression does, which is what we saw in a previous video. So for a person I, their response to an item is a function of the intercept plus their latent trait score, but only to some extent. This is quantified by this weight of the item, which would come here, plus the error. the weight of the item, which I was saying would be depicted as some kind of regression coefficient here, is known as the factor loading. Quick question, what do you think the intercept represents? Have a little think of what it represented in the context of regression when we had the outcome variable, a function of the intercept, plus the regression strength times the predictor, plus some error. Alright, so in linear regression, the intercept represented the expected level of the outcome when the predictor had a score of 0. Now, there's no reason why it shouldn't be exactly the same here, and this is exactly what it means. But there is a nuance here, which is that for factors, it is considered that a score of 0 represents the average score. So what this means in terms of the intercept is that it is the level of the outcome variable that you expect for someone with an average level on the latent trait. So in our specific example here, let's say that we are interested in item 1, so this one. I'm interested in other people. The intercept would represent the score a person would get on this item if they had an average level of happiness. What about this? Why do we need a weight of item thing to qualify the effect of the latent trait score? How do you think this matches up with what we know from regression? Right, so the weight of the item is kind of like the slope in a linear regression, what we knew as the beta coefficient when we had standardized results. In the case of factor analysis, we usually depict this with the symbol lambda, and we call it a factor loading. So these paths would be labeled lambda. Now, the whole purpose of this analysis is to obtain scores on happiness. Let's call these factor scores, because they are scores on the factor. But why would we even want to obtain factor scores in the first place? The obvious first reason is that you would like to minimize the number of variables that go into your model, because if you were to put the items straight up, then you would have so many highly correlated predictors, and these correlations would first of all create issues of multicollinearity, whereby you wouldn't be able to tell with certainty which one is the true predictor. But of course, there's the compounded problem that these could actually all be manifestations of the same underlying thing. Even so, you might wonder, why shouldn't I just compute a total score in the form of an average score or a sum score? So let's have a look at how these two differ. So one of the assumptions of sum scores is that the questionnaire items are pure and contain no error. In contrast, factor analysis assumes that responses to an item are to some extent explained by the underlying trait and to some extent explained by other things which we label error. One can say that factor analysis partials out error. A second assumption is that all items are equally important. So when you sum up your scores, or when you then take the average by dividing by the number of items, you are actually counting them all as equally important. In contrast, in factor analysis, you have included different weights for the items, the factor loadings. This helps determine which items are stronger or purer manifestations of the underlying trait. So, for example, if you have a questionnaire about depression, you would probably understand why the item about suicidal thoughts should have a bigger loading, a bigger weight, than the item about feeling fatigue. That's because the item about fatigue could be a manifestation of other things as well. However, the item about suicidal thoughts is very much likely to be a manifestation of depression. Now, factor analysis comes in two flavors: confirmatory or exploratory factor analysis. So let's have a look at the framework and how these two differ.